So we've got 5 speakers. They'll go for about 20 minutes each with about 5 minutes of Q&A. Starting first is Peter Lloyd, who's going to talk about quantum measurement and mental monism. Take it away, Peter.
So this is about mental monism, otherwise known as subjective idealism, the theory that everything is mental. Hopefully the slides will pop up in a second. Thank you. So I'll be starting with the hard problem, as always, and do a bit of linguistic philosophy, out of which will pop mental monism, the theory that the whole of reality consists of conscious mind and nothing else. There's no physical world. Derived from that hypothesis of what I call unitary consciousness. And meanwhile, we'll look at the measurement problem with its attendant wave collapse, and particularly look at Wigner's friend experiment, thought experiment, and then use the unitary consciousness hypothesis to rescue Wigner's friend. Now, I know from past experience that often people hear what they expect to hear, not what is actually said. And a lot of people will come out of this room thinking that I've said this, that because of Wigner's friend, therefore the world doesn't exist. No, that's rubbish. I'm not saying it. I'm saying this, that mental monism has its own philosophical foundation, and it's then being applied to the physics problem of wave collapse. So a little bit of history. Obviously, this starts off with René Descartes and the mind-body problem, which is rebranded by David Chalmers, the hard problem of consciousness. There are 4 basic solutions to it. Physical monism, the idea that there's no consciousness. Dualism, that there's physics, physical world and a mental world. Mental monism, there's only consciousness. And Mysterianism, that we haven't got a clue. Now, physical monism doesn't work because it excludes the explanandum, it excludes consciousness. Dualism doesn't work because it assumes there's a physical world, which, as we shall see, there isn't. And Mysterianism doesn't get us anywhere, so let's forget about it. Mental monism isn't new. Adi Shankara developed this theory within the Advaita Vedanta system in the 8th century, and George Berkeley, 1,000 years later, came up with essentially the same key idea that there's nothing but consciousness in the world. Shankara also put forward the notion that the Atman, or personal soul, is numerically identical with the Brahman, or universal soul. In other words, there's one single consciousness for all sentient beings. Berkeley never arrived at this conclusion, but I will argue that it is implicit in the logic of mental monism. Our modern sage, David Chalmers, has said that mental monism, there is a non-negligible probability that it's true. So we should be grateful for small mercies. I'll give, in a nutshell, the proof of mental monism. Obviously, that won't convince anyone because it's a very short bullet point description of it. It's not a new argument. It's been developed by Berkeley himself, 1710, John Foster in the 80s, Kenneth Peirce more recently. My own 53-page version is online. What I'm going to give you is basically a 2-page bullet summary of it. The argument's got 2 limbs addressing these questions. Is the conscious world physical? And secondly, can the physical world exist anyway? And leads to the conclusion of mental monism that reality consists of only conscious minds. So here's the first limb of the argument. Physical terms are derived analytically from undefined fundamentals. For example, an atom is made out of electrons, protons, and neutrons. An electron is made out of electric charge and mass. Mass and charge are undefined fundamentals. Any physical theory has this characteristic. There are undefined fundamentals at the bottom, and everything else built up analytically from them. Conscious terms, on the other hand, derive from private or sensitive definition. For example, if I want to show you what post office red is, I'll give you a sample of that color. You'll see it and say, okay, that is what we call post office red. Same with all other colors, smells, taste. You have the experience and you label the experience. So you have 2 disjoint lexicons. The lexicon derived from fundamentals, undefined fundamentals, and the lexicon derived from experiences. And physical propositions are expressed in that lexicon of physics and will never enable you to infer any proposition expressed in consciousness. Therefore, all mental facts are non-physical. Second limb, a term can make reference only to what is known. For example, the word red. You can refer to red only if you've experienced it, if you've known it. And so in general, the non-mental world is, okay, so in general, you can only refer to things that you know, but the non-mental world is something you can't know, therefore you can't refer to it. Therefore, the existence of a non-mental world cannot meaningfully be asserted, and therefore a non-mental physical world cannot exist. So the general conclusion is the conscious world is non-physical, and no physical world can exist, hence mental monism. No one's going to be convinced that by that because it's very fast, but it gives you an outline of what the full argument is over 53 pages if you go online. So enough of metaphysics, now look at some modeling. In physicalism, the dynamics and structure of the mind are driven obviously by the brain. In mental monism, there is no brain. And so the mind has to bootstrap itself out of its own existence. And not only the mind, but the brain, because the whole physical world is a construct which has to be bootstrapped out of the structure and dynamics of the conscious mind. So the whole world has to come out of whatever we regard as the model of consciousness. Now this modeling of consciousness requires two distinct models, one of which is what I call the experiential model, and the other is the interface model. Why do we need formal models for this anyway? Well, one of the common criticisms of subjective idealism is that it's all a bit silly, that there's a magical deus ex machina, or it involves woo-woo chicanery, or in Dan Dennett's terms, a reversion to pre-modern unscientific dark age thinking. Obviously, we don't want any of those. So we need to formulate a naturalistic, objective model of how consciousness works within mental monism. So mental monism says there are only minds in existence, your mind, my mind, and some kind of background consciousness. Berkeley called it God, Shankara called it Brahman. I'm using the term meta-mind as a non-religious term referring to this background consciousness that runs the physical world. And the physical world is a construct derived from this realm of consciousness. It includes avatars, which are our bodies, enabling us to communicate with each other and with the rest of the construct. The experiential model will describe how the conscious system works. That is, I've outlined that in a paper in Entropy Journal year before last. And what I'm talking about here is part of the interface model. How does the physical construct interact with the realm of consciousness? So our first premise is mental monism, that reality consists of a countable number of minds, M0, M1, etc. And one of the corollaries of this is that is non-spatiality, that minds are not in a spatial medium. And that has implications for our modeling of how the realm of consciousness actually operates. In particular, individuation of minds. So in physical realism, we each have a brain in a different position in space, and that individuates our mind. So your mind is different from mine because the brain is in a different place. Let's just pause for a moment, look at some terminology. The brain obviously is a lump of tissue inside your head. The contents of the mind are the experiences and volitions, phenomenal color, smell, pain, intention to raise your hand, thoughts, etc. And the subject is whatever it's doing, those acts of experience or volition. Now, is the subject a real thing, or is it just a notional domain in which all these experiences happen? I know a lot of people really believe the subject exists. I tend to follow David Hume's notion that it's a construct. Doesn't really matter, because what we're looking at here, or will be looking at, is not what the subject is, but how many subjects. So take your pick. Nothing in the following hangs on your interpretation of the nature of the subject. So getting back to this picture, the brains are separated by distance, hence the mind and the subject are also individuated by the spatial separation of brains. In mental monism, there are no brains, and so there's no distance between minds. Minds are individuated by access to the contents. I can access all the experiences in my mind. You can access what's in your mind, but not mine. So the picture is that the universal set of experiences is partitioned into separate areas of experiences, each of which is bound by access, and that individuates the contents of the conscious minds. The subject, on the other hand, has no content. It's simply what is witnessing these experiences. So there's no distance between different subjects, no difference of content, so there's no individuation. And if you can't individuate different subjects, then it's just one subject, which brings us back to Shankara in the 8th century, saying there's only one consciousness for all beings, all minds. Even though we see and hear different things, therefore we have different contents, the consciousness is unitary. Sorry. So enough of metaphysics, let's get on to some physics. Consider a box containing a quantum system and an observer. The observer measures it, the quantum wave function in that box collapses, and out pops the result. I'm not going to be considering parallel universes or all that stuff, simply assuming that the wave function actually objectively collapses. I skip over Schrodinger's cat because everyone knows about it and go directly to Wigner's friend. So here's Wigner's friend stuck inside a box with a quantum device and a light bulb, which indicates the output from this quantum measuring device. We don't want to be killing people with cyanide as in the original experiment. Now, as long as we consider this box on its own, everything's fine. So here, the quantum device is measured to be having a direction to the right and gives you a green light. If it was pointing the other way, we get a red light. The Wigner's friend sees this, his consciousness recognizes it, there's no problem at all. The problem arises when we look at it from Wigner's point of view outside the box. From his point of view, the contents of the whole box goes into a superposition, and we have a problem of what on earth is happening in his mind, in the mind of his friend. So once Wigner opens the box, then the wave function of the whole box collapses, and we get a straightforward result. Either there was a measurement to the right, and we have a green light, or a measurement to the left, and we get a red light. And Wigner can ask his friend, well, what did you see? And he'll give a correct answer corresponding to what Wigner sees himself as being the light bulb. No problem at all. But it's only a problem as long as Wigner is a non-realist about consciousness. If Wigner is a realist about consciousness and says that Wigner's friend has a real conscious mind that is in some state or other, then there's a problem. Because quantum mechanics applied to Wigner's friend says that the wave function has collapsed as soon as Wigner's friend measures the device inside the box. But quantum mechanics also says that his friend doesn't collapse the wave function until Wigner opens the box and measures it from the outside. So this is really the elephant in the room. It's a contradiction in quantum mechanics, not one of numerical results. Obviously, quantum mechanics is a wonderfully precise and reliable theory, but in terms of its predictions for mental states. If we assume realism about consciousness, then quantum mechanics is self-contradictory. So what's the answer? Well, as we saw earlier, according to mental monism, there's an implication that everyone's consciousness is the same. So Wigner's consciousness is the same as his friend's consciousness, even though the contents of the mind will obviously be different. So therefore, when Wigner's friend measures the quantum device inside the box, that will collapse the wave function of the whole box. And when Wigner opens the box to look inside, nothing happens because the wave function has already been collapsed by Wigner's friend. So there is now no contradiction between quantum mechanics applied by Wigner and quantum mechanics applied by his friend inside the box. So the proposal is that whenever a wave function is collapsed by one conscious observer, then it's collapsed for all conscious observers. I know this is a bit crazy, but at least it provides an internally consistent solution to Wigner's friend problem. And the effect is the same as making conscious observation a superposition blocker, but at least it gives a reason for it to be a superposition blocker. Of course, zombies and limited physicists don't care about this anyway, because they don't believe Wigner's friend has got a mind. But 2018, two Swiss physicists published a blueprint for a zombie detection device. Frautschicker and Renner published a paper about basically a double-barrel Wigner's friend experiment. Now that paper is full of mathematical physics I don't have time to go into here, so what I'm going to describe is a fantasy experiment which captures the relevant philosophical idea of Frautschicker and Renner's paper. So instead of one box, I have two boxes, so I labeled Lou and Lei. Instead of Wigner, I use the letter W, but Wu and Wei, and the person inside, Fu and Fei. The initial experiment in the first box involves measuring a quantum device, which the result of which I will label either heads or tails. And Fu will set up a particle, either spin down or a superposition of up and down, based upon whether he gets head or tails from the initial measurement. He then sends that particle into the other box, into Lei's box, where Fei will measure it and find it, measure it according to the relevant basis and find it to be either spin up or spin down. And relevant light pops up. Now, when Wu measures that first box, Lu, up until that point, according to quantum physics, the whole of the Lu box will have been in a superposition. And this whole episode of creating the particle and sending it over to Lei will not have happened, in a sense. Because at the point where Wu opens the box, at that point, there's still a 50-50 chance of getting heads or tails. Meanwhile, in the past, as it were, the particle was received by Fei, and it's possible that the initial coin was tails. Fei got that superposition of the two up and down, and when he measured it, got the upward spin and got a red light. So it's possible to have a result where Wu finds that inside the first box there's a head, whereas Wei finds the second box there's a red light, which is impossible because with a head coin, you only get the spin down particle. And with that, you don't get the red light. So there's a contradiction in the possible results in this experiment. Now, if we go back to this notion, this crazy notion that all consciousnesses are one, then we find that Fu has the same consciousness as Wu. And when Fu takes his measurement inside the box, that collapses the wave function of the box. And so we don't have the possibility of this contradictory result. And that's it.
Hello. Okay. So I've noticed with a lot of idealists, and I even lean in that direction. I've seen this kind of recurring computer science metaphors being used recently, and one is a term that you use is kind of thinking of it as this one consciousness that's partitioned itself. So for me, this is where I get stuck in idealism, and I haven't met anyone who's been able to answer it using computer science metaphors. And maybe this is a case of using physical terms, right, that don't apply. But how does a non-material, non-tangible consciousness encode reality? I mean, we live in a structured world with, I mean, it has to be able to store information.
Yeah.
So without, when we're on a computer and we're like there's fundamental, there's like electrons, there's a substrate. So without a substrate, how does consciousness encode and store information? Does that make any sense?
Yeah, I think the answer is that consciousness is the substrate, that if we drill down into the world, then we find that there are structures built up of smaller units of consciousness. And at the bottom, there must be some very simple units of consciousness, which are the same kind of things we have in our phenomenal experience, like colors. We can't imagine what it's like to actually be at that base level because they're so different from our experiences, but they are the same nature as our experiences. And those units of consciousness must have certain laws for how they interact. I imagine it to be similar to a cellular automaton, where there's this universe domain. It's not a space because there's no space there, but a domain of units of consciousness which can relate to each other and form complex structures in the same way that in the game of life, from that very simple logic of those squares in the game of life which can interact, you can build entire Turing machines. So I don't think there's in principle an impossibility that from this base level of small units of consciousness, we could construct the mind and construct the whole physical universe.
But this substrate you're describing, and I'm sorry, but it's not a material substrate. It's not a tangible. So is this more or less like a conceptual substrate?
No, it's made of consciousness.
So it's like beyond science, basically.
So sorry?
Again, I lean idealism. This is like an honest, genuine question. So it's just, it's a non-material substrate.
Yeah, it's a non-material substrate. That doesn't mean that it's not concrete. I mean, when you stub your toe against the bed, that pain is a real concrete objective thing in your mind. Likewise, these basic units of consciousness are real concrete things, but they're not material. So there is a concrete substrate, but it's a non-material substrate.
Thank you.
Okay.
Yeah, it's a very nice way of solution for the quantum measurement problem. But isn't it so that all the different possible ways of resolving that, for instance, the objective reduction of Penrose, that has the same goal and the same result, because then also it is reduced. And when it is reduced, there is not another friend of Wigner needed.
Sorry, could you say the first bit of that again?
Okay, if you have the objective reduction,
yeah,
or orchestrated or not,
yeah,
then the superposition is also reduced, collapsed.
yes.
Okay, so then you have also a solution.
No, because even with that kind of objective reduction, there's a problem of what happens to the mind of Wigner's friend inside the box. From the point of view of the person outside the box, Wigner's friend in the box is now in a superposition.
No, not necessarily, only in a dogmatic way of physics. If you believe in the objective reduction,
okay, so right, yeah, so that would be an alternative solution, but then that requires a change to quantum physics to have an objective reduction. I mean, Roger Penrose's notion that gravity pulls down the bubble of superposition, which is a possible solution, but then that requires a different physics. I mean, at the moment, quantum physics doesn't have that gravitational collapse, whereas this theory doesn't require a change to physics. It requires a change in the interpretation of it.
Okay, that's it.
But yeah, I'm not saying this is the only possible solution. It's just one that specifically addresses the problem of other minds, which is something that physicists often don't look at because consciousness is pushed to one side. And I think that we shouldn't be ignoring the problem of just what happens to Wigner's friend inside.
Hopefully it's quick. What level of consciousness is required in this? You got Wigner and Wigner's friend, but I'm talking about trees falling in the woods and maybe squirrels in the tree or insects. What level of consciousness is needed for this collapse?
I would assume that any level of consciousness.
If it's a measurement, it doesn't have to be a super specific measurement, any measurement.
Yeah, I mean, if the signal is a red light or green light, then any organism which could have a conscious experience of that image would do the trick.
I agree that there's this explanatory gap, and thanks for your attempt to fill it. I have a question though. We do know that people have individual experiences of their own consciousness, as you mentioned, regardless of whether you're a monist or not. Presumably, if I stub my toe, you're not feeling it. So how does your model explain, or does it not yet explain, the individuation as well as the unitary piece?
Yeah, it's a good question. I didn't have time to cover that in this talk. There's a separate talk to give on Sunday. Also, in my paper in the Entropy Journal, it goes into more detail. The answer is that, I don't know how to put it very simply, essentially each mind is separate and partitioned separately, but there will be channels of communication between them in which one mind overlaps with another, and a volition in one mind constitutes an experience in another mind. So there are structured points of contact and communication between the minds. Otherwise, we wouldn't be able to share the same construct. I know you want to have a more detailed explanation. I can't fit that into this question, but yeah, it's a very good point.
So yeah, you're just saying you have an entropy paper. Has it come out yet?
I'm sorry?
Has your entropy paper come out yet?
Yes, it's published 2020 in the Entropy Journal.
Okay.
Great. Okay. So I'm James Tagg from Balance Corp. And I'm going to report on an experiment that we've just done to see if we can test objective reduction with some largish mirrors. So very kindly, UCSD offers us some space, and then COVID hit. And so we in fact had to build the experiment in my garage. So we've just spent best part of 2 years in my garage working on this experiment. So just ignore the bit on the left for the moment. We understand, I think, that the double slit experiment, we have some light that comes through it, goes through a double slit, we get an interference pattern. Okay, so here's a thought experiment. Let's have a single photon arrive and go through a half-silvered mirror, get split in two, quantum-wise, we'll do that in detail later. And then we have that photon detected by two detectors, amplified by two amplifiers, connected to two little motors. We actually use piezo's, but two little motors, and it pulls the two shutters off the mirror, right? And so the question then is, do we see an interference pattern or not? Or does one mirror open and the other one doesn't? And the question, so this is a thought experiment, so I can play some games at the moment. So it probably can't happen in the detectors, because I can, in principle, put these many light years, 6 billion light years away, and the experiment will still work. And I can do the same with the amplifiers. I can put them billions of light years away, and they'll still work. And that's the delayed choice quantum eraser type of experiments, right? Cosmic quantum eraser. But obviously, it's got to come back to do the actual interference pattern. So it's probably got to fail in the motors or in the shutters. So the Penrose idea is that it's gravity, right? So that basically the shutters weigh some weight, and when they move, it causes a paradox in space-time, and that paradox gets resolved in a certain amount of time by one of the shutters moving or the other moves. But of course, that leaves an interesting thing, which is for a short period of time, I'm going to see an interference pattern, and then that interference pattern is going to go away because it takes time to collapse. How long does it take to collapse? Well, very, very kindly, Roger and some colleagues in England actually calculated in a lot of detail how long the collapse takes. And there are two main cases. One where you take two things and you move them apart a long distance. And the other one is where you move them apart a very short distance. Now, the advantage of the very short distance, you can take a large thing and move it a very short distance, is that's a squared term. So if you take that large thing and you move it just 40 angstroms, that gets squared, which is an even smaller number. And so actually that means that you get quite a long time. And in fact, we calculate that the time for a 0.2 gram mirror moved just 40 angstroms is about 1.2 microseconds. Now, the nice thing about 1.2 microseconds is my lab oscilloscope will measure that. That's just a megahertz, right? Lots of electronics and stuff will measure in that region. So this is indeed what we did. We built a 0.2 gram mirror and attached it to a piezo. It was a motor, and attached all of the things we just described. In fact, we have obviously 2 mirrors, and it's a symmetrical experiment. And for a whole bunch of experiment reasons, we have to put that on an air table and in a Faraday cage, and everything's in a Faraday cage and all isolated and so on. So we now need to get some superposition going. And there's lots of ways now. I mean, there's 100 quantum computing companies, and they're all putting stuff into superposition all day, right? So it's now very easy to put in things in superposition. The obvious one, and the one that most people use, is some sort of superconducting spinning current, but you can use photons, you can use ions. I mean, just a legion of things. Photons are the most fun thing to use because you can do really weird things with photons. First of all, normally when we think about quantum state, we think about something that's like spin up and spin down at the same time. So it's in one place, right? Conveniently in one place. And we can, as humans, go, that's a qubit, and we can point at it and it's in one place. But with a photon, when you split it in a half-soldered mirror, it delocalizes, and it can delocalize at 6 billion light years, and we know that from delayed choice, right? It can do even more weird things. There's a Cheshire cat problem where a bunch of researchers took it, split the photon spatially, and also split the spin. And you can measure the spin and the spatial independently. So you can actually have the grin in one place and the cat in another. Okay, now we'll come back from some very esoteric stuff and just do kind of slightly more boring. So we take a photon and we delocalize it. So it goes around 2 halves of a Mach Zehnder, and it's delocalized a short distance where you saw my experiment. It's like a couple of feet, right? Not too much, and it comes back. And then we control the 2 arms of the Mach Zehnder. So we have a photon from a diode laser, comes into a beam splitter, we split it, we detect it with 2 single photon avalanche diodes. They generate quite a lot of current. We use that current to drive 2 motors, which drive 2 mirrors. What we see then is an interference pattern, because it's a Mach Zehnder, and we see it, and Will Reid, who's done this experiment with me, is an absolute expert in calibrating these things. It takes me 14 hours to calibrate a Mach Zehnder. It takes him 14 minutes. So obviously he does it always. So what happens? Well, what happens is that if a photon goes down 1 arm, then that arm shortens and the yellow waveform moves to the right. And if the other arm shortens, it goes down the red wire, and the red photon, as it were, moves to the right, okay? And so you get a differential. Now, normally, if it detected it, you detect one photon or the other, you get differential movement of the 2 things, and you would see the interference pattern change. Now, if they're in superposition, for a short period of time at the beginning of the experiment, both mirrors will move, everything will be in superposition, and you won't get a change in the interference pattern. So you get a delay in the change in the interference pattern. Now, how do you control for that? Well, it turns out if you turn the laser off, the diode laser in the fridge, you just switch it off, you still get hits from the SPADs because there's dark count coming in. So you'll get occasional firings, but they're never superposed because there was no photon that was split. They're just random. So that gives you a nice control. It says, if I have photons that are not superposed, I get one curve. And if I have photons that are superposed, I get another curve. So we put our diode laser in a refrigerator. This is the only bit of the experiment that has to be done cold. And that's simply because dark count is proportional to temperature. And if you cool it down to -10 degrees C, you just get 1,000th of the dark count. So the experiment it's a nicer experiment, but you don't need to do it. Then we set up our experiment. it's now a little bit prettier because we've got a lab. So we have our refrigerator and so on. We can look at the outputs. Now, if you were looking at my first version of this diagram, okay, earlier, you'll see that there's in fact a problem in it. And the problem is this, which is if one arm shortens, the signal goes up. If the other arm shortens, the signals goes down. I can therefore look at the output of the experiment and say, oh, the photon went left or the photon went right, okay? I've got knowledge. The oscilloscope, the measuring everything, my brain, is in a paradox, okay? I have a lot of mass. I'm going to collapse the experiment. Even if I do something weird, like try and store the experimental results in the oscilloscope and don't actually look at them to try and reduce the mass, if I store them anywhere and write them down, an alien in 6 billion years' time can maybe look at that data, see which way it went, it will collapse, and it will collapse all the way back to today. That's delayed choice. So we must erase the information completely. This is the standard quantum eraser. So we erase the information completely by just flipping one of the mirrors, one of the motors on the mirror. So the mirror now goes down when it would have gone up. Okay, just very simple. The difficulty is your brain will now explode, because I just said that the good thing is if it's delayed, right? Now I've flipped it with a quantum eraser. The good thing if it happens faster, okay? Took me a couple of months to get my head around that, but that's what's going on. And then we have to have a second quantum eraser because we want to actually start the experiment. And if we connect an oscilloscope to the laser, you know, firing, and we put, you know, yellow channel on one and red channel on the other, we've got knowledge of which way the photon went, so we've destroyed it. But the very, very simple thing to do is just to connect both scope probes to the same channel. Now, as a summing junction, you see a waveform, you have no idea which way the photon went. You can see that two photons went. In this diagram, you can see this yellow channel, that's the first photon arriving, and you can see on this experiment, a second photon arrives as well within the same thing. Obviously, it's all random because it's a quantum process. It's just randomly happening. So I get a single photon comes in, and I move my mirror. Now, the big question here is decoherence, right? This experiment should not work because the decoherence time for our experiment is 10 to the minus 18 seconds if you're very, very, very generous, and 10 to the minus 30 seconds if you're sort of realistic, which is tiny. But if you look at the maths of decoherence, you start out in our quantum system that we built earlier and say, well, okay, I've got a density matrix, and my density matrix is a half, some sort of phase term and a half. If it decoheres, the phase terms tend to zero. So I lose my phase information. I don't know what the phase of it is. I can no longer do quantum computing. It's junk, probably, right? But it's still symmetrical. It hasn't collapsed. It's still a half, zero, zero, half. In fact, it's more symmetrical than when it was a quantum state. It's now in a state which is neither classical nor quantum. In order for us to get a result from the experiment, it must collapse. It must be 1001, sorry, 10000, or it must be 0001. It's got to be in a classical collapse state. And so until we collapse, our experiment doesn't lose its symmetry. We don't care if it's decohered because decoherence is symmetrical. So we've done a kind of Cheshire Cat trick on it. We've separated decoherence from collapse. So what's the result? We get a positive result, okay? So basically, it takes some time from the start of experiment where you compare the control, which is no laser, to the superposition before they come together. In fact, it takes about 1.4 microseconds, which is approximately the number that's calculated in the Howell, Penrose, Fuentes paper. So it kind of matches the theory. What are my problems? Well, my problems are, I showed you a lovely smooth graph. Actually, of course, all our data is quite noisy. So we have quite a lot of noise. At the moment, it's quite high impedance before the experiment. So it picks up a lot of radio frequency noise, even though it's in a really good Faraday cage and so on. And we get some errors. We get some things where the thing drifts. We have no drift correction. We haven't had the money to do some cool things to get out of all those sort of things. But it's statistically significant and it's repeatable. We can do the experiment 10 times and 8 of the times, odd, it will work, and 2 of them there'll be junk, and we have to go and look at the junk and go, oh God, what, why was there junk? And that takes another week to kind of parse through it, but it's sort of kind of going well. What would we like to do in the future? We'd like to modulate the mass, either in real time, I switch the mass up and down, which we can do with just standard electronic switches to switch in more mass. We could substitute, very coolly, living matter. So we could actually put mini brains in. We could use some sort of living tissue to detect the photons. So at UCSD, they have mini brains that have retina. The retina is sensitive to a single photon. They amplify it up. They do some stuff. We can look at the stuff that they do, and we can use that to move the mirrors. So we can separate, we can remove a SPAD and insert a sort of organic SPAD. Final kind of thing that we would like to look at, and we are way too noisy to do this, but if you think about Roger's theory, and it's proportional to E sub G, it's a probability that it will collapse. Well, that probability could be, in a billion years' time, it still hasn't collapsed. So in principle, it's still a many universes theory, right? Some people might like it, some might not like it, but it's still kind of a many universes theory. And that's because you've got a probability distribution, you've got an area under the curve, and that, because the curve goes on to infinity, that could be an infinite area. And that's the problem you had with a microwave catastrophe. And so what you had to do is introduce quantum mechanics into electromagnetism in order to avoid basic black body radiation not working. So I think we will need to look at some sort of quantization of collapse as opposed to it being a smooth function. And that will be a nice thing to sort of look for in the data. So that is my talk and my result.
And on your last slide, quantum physics doesn't solve your problem because it's just like radioactive decay. You've got a half-life from your T, but then there's an exponential decay.
I am looking for help on that point. I don't understand that point. Hi.
Hi. So just in the most basic sense you can answer, I've got 2 questions for you. One, what could you do with this phenomenon? Right? What are potential applications that you're willing to share? And and 2, how do you put mirrors into how do you put a mirror into superposition?
Okay, so second question first, because it's easier. How do you put a mirror into superposition? You work on it really, really hard for 2 years of your life. Basically, if you've got a photon, which you can easily put into superposition, it's now in superposition. If you amplify the 2 legs of that up and control 2 mirrors, both mirrors are going to do the same thing unless there is collapse. So you've put the 2 mirrors into remember, this is a symmetrical experiment where we've used photons and we've delocalized it. So you have to sort of kind of think about the mirror being kind of one thing, right? It's part of one system which is in superposition. So the 2 mirrors have in some sense, shared superposition. The first question, applications. Patents not filed, can't tell you. Will is looking at me glowering. All sorts of things. Basically, you've got a new type of quantum computer. So actually there is a slide. Oh, okay. But it's a new type of quantum computer. So classical explanation for lock and key mechanism in drug discovery is that the thing bounces around until it locks. Quantum is, it bounces around in superposition, tries everything, finds the lowest thing by gradient descent. But what makes the decision? At the moment, we think that the decision for whether the drug binds in your body is the doctor observing that you got well, or if you're conscious and not, under sedation, you observing that you got well, right? That's the sort of conceptual, but actually the drug should dock if it reaches a certain quantum gravitational level, and it should react, and that should be it. So one of the applications is looking at the way that drugs interact with the body. That's the least imminent one.
So I didn't quite follow this argument you made about warding off this problem of decoherence. It was something along the lines of your reduced density matrix is taking a certain form, but it remains symmetric. And for that reason, it's no longer a problem. And I didn't quite follow that, because whether or not it remains symmetric, it's still the case that it's decohered because there's entanglement with the environment, which should trigger the condition for collapse anyway. So could you just say a little bit more about why that was a way of removing the decoherence problem?
Okay, so in a survey done mainly in Denmark of physicists, more physicists than not believed that the collapse problem had been solved by decoherence. But in general, that's a wrong view, right? So that collapse and decoherence are two separate things. So I think in our experiment, what we do is we are sensitive to collapse. The system has to go left or right. If the system's lost phase information, it's still symmetrical, which means that our interference pattern is not going to move, because it can only move if it's come asymmetrical. So I don't care whether the thing is, noisy as hell. I care about its noise because of classical noise, because I find it difficult to measure. But if it's basically just lost all phase information, that's not collapsed it, and it's not gone asymmetric. So that's the Cheshire Cat trick. By delocalizing the photon, I separate where it is and what phase it is. And I care where it is. I don't actually care about the phase. So if you read the Cheshire Cat paper, and the last thing we did before COVID was we flew to India and we met the Cheshire Cat paper writer and talked this through in quite a lot of detail. That's the paper to go and look at, to kind of see that you can separate different bits of a photon's quantum state. And we use the fact you can separate them to separate decoherence and collapse, we think, right?
So our next speaker is Thomas Brophy, who's going to talk to us about quantum collapse property dualism A theory.
Okay, I'm with California Institute for Human Science, and let's go into this. Actual theory is what I call a meta-ontology of approaches to the consciousness causation problem. And I started calling it actual theory, sort of tongue-in-cheek, actual, but actual is meant to be what actually happens. Trying to get at what actually happens. So in this talk, I'm going to do a little bit of a brief about the motivation for developing this project, and then talk about types of property dualism. And I'm going to be drawing a lot from Chalmers and McQueen's paper, our host of this session, that's coming out in a book chapter, but was published on ArchiveX already. And I'll talk a little bit about actual theory type of property dualism and categories of problems that can be addressed this way. So on the motivation, early experiences of anomalous cognition of myself were incongruent with a physicalist worldview. So did a lot of meditation practice and studied physics and had a kind of a white crow experience, right? It was kind of a visualization, visceral experience of there's no problem with the, I was very concerned for many decades with the idea that the physical universe is causally closed, therefore consciousness cannot have any effect in the world. That didn't seem right to me. But the arguments seem to make that the case. But then I had a kind of experience of why that's not the case. So this is what this project really arises out of. So it's initially a quest to explain how anomalous consciousness works, but that evolved into a question of trying to solve or trying to address even ordinary conscious action. How does that happen? And I first presented at the Tucson poster in 1998. And that was about the time that Hiroshi Motoyama invited me to CIHS as well. And I wrote that kind of experiential idea that I mentioned in a book, The Mechanism to Advance of Mysticism. And then in 2018, Tucson, I started developing this approach that I'm talking about today. And I presented it also a little bit at the Society for Consciousness Studies, which I encourage everyone to join, sort of a sister group to this one. And last year, finally, California Institute for Human Science was accredited. So the scientific motivation for this, I see as really the central unsolved problem of modern science is the mind-body problem. What is the relationship between consciousness and physical processes? I think that's really the central unsolved problem. And also, Hiroshi Motoyama's, the founder of CIHS, California Institute for Human Science, Hiroshi Motoyama's mission for CIHS as a university, it includes basically addressing this problem. He's got eight principles which form the CIHS's mission, and 3 of them are really appropriate here. These are Motoyama's principles, which are part of the mission for CIHS: to understand human existence from the total perspective of body, mind, and spirit, to elucidate the mechanism of the correlation between mind and body, and to actualize mental control over body and matter with the resulting better life, and to establish a creative science that researches the mind and soul as well as matter. Motoyama was also informed as well by direct experience through through yogic meditation practices, and in his book Being and Logic of Interactive Function, he lays out this view that there's a developmental experiential process through meditation of a series of negations of the metaphysical self, which is a unity of more and more selves, and eventually all consciousnesses are in a sense one, sort of like Sankara we were hearing about earlier, and he takes it further to absolute nothing. So the absolute nothing stage, it violates Aristotelian logic because it has to be being and not being at the same time. And the way Motoyama describes that is similar to the way some of the ancients described it as well. It's really, it can be seen as a metaphor for how Bohr and Heisenberg described the Copenhagen interpretation of quantum mechanics. So question is, can actual theory be a foundation for going beyond just a metaphor, that being just a metaphor? So thanks a lot to Chalmers and McQueen, because this approach now draws a lot on their paper. And I think it really sets a firm theoretical framework or foundation from which we can jump off. And basically, I'm advocating for what they set out is a possibility, but then they say, well, we're not prepared to go that way now. So a little bit of history as I see it, Tucson, these conferences, back in 1998, quantum effects were believed not possible in the brain. classical physicalist models were viewed as really the only scientific approach to consciousness. Causal closure of the physical was generally accepted. Now, quantum effects of many types are known throughout biology and the brain. There's still, as we heard this morning, a lot of skepticism about mesoscale quantum effects, but that's sort of a skeptical view now, not the standard. And quantum physics necessarily is related to consciousness. We know that from physics, actually. And if conscious physical agency happens, it involves quantum collapse. It's kind of a standard view now, and actually in Monday's workshop, Johannes Kleiner talked about a proof that actually if conscious agency happens, the only way it can happen is through the collapse process. And now there are very many panpsychists, pan-experientialists here at the Tucson conferences, and causal closure of the physical is being relinquished. So the physicalist claim is something like this. Interactionalist dualist theories of consciousness are impossible because they violate the law of conservation of energy. The physical universe must be causally closed, therefore consciousness cannot have causal agency. But that's not necessarily true. It's nothing in foundations of physics that says that. So there are heuristic arguments about this, but there are also now proofs along these lines. So I'm not going to go into this. It's pretty well known, but you have the standard quantum textbook quantum mechanics where the wave function evolves according to the Schrodinger equation, and then you have a different process, non-deterministic process of collapse. And the collapse is onto one of the eigenstates. All the eigenstates have the same total energy, so there's nothing there that violates conservation of energy, but you have very different outcomes. So is consciousness a series of unique single events? What is the actual reality that Bornwell rises out of? What is the universe doing? Standard quantum physics says nothing about unique single events, right? Nothing about unique single events, except the probability distribution. But a lot of what is interesting about reality may actually be unique single events, not infinite ensembles of identical probabilistic events, like a world record pole vault, perhaps. But a lot of human events, maybe in a sense, unique single events. But okay, back to this approach. So in a nice YouTube video, Chalmers gives a general audience view of their paper. Materialism is the view that everything, including mind, is physical, physics only. Dualism is the alternative to materialism on this view, and everything is physical or mental, and mind is non-physical. You have substance dualism, where substance is things. The world contains both physical things and mental things, like Descartes' approach, and property dualism, which is the main subject here, in which there's only one kind of thing, but two kinds of properties. So Chalmers points out that on his approach, property dualism is more compatible with science than substance dualism, because there are no souls in property dualism like substance dualism is. I'm not so sure about that argument for why it's more compatible with science, but anyhow. The fundamental properties of science on this view are governed by fundamental laws of reality, like quantum mechanics, relativity theory, etc. And an example of introducing a new property is James Clerk Maxwell introduced the property of charge. Electric charge is a fundamental property governed by Maxwell's laws of electrodynamics. The traditional objection to property dualism is the physics is a closed system objection. But causal closure of the physical is not, it's really a pre-theoretical notion. It's not entailed in physics. The physical universe is not necessarily causally closed. Okay. So back to Chalmers-McQueen's approach. They use Tononi's integrated information theory, specifically the Q shapes of phi as the consciousness property that triggers the collapse of the wave function. And then they develop a quantum mechanical wave function collapse mathematics for applying the Q-shaped consciousness property causing collapse. The challenges, and they point this out in their paper, the challenges or problems include the following with the model that they're doing. The consciousness property on this model is Q-shaped. And what is it that IIT Q-shapes actually are a measure of? They seem to be a measure of the physical system. And what is it doing the integrating in IIT? It's questionable if this approach addresses the consciousness causation problem, as Chalmers points out in their paper. And this is a quote from the paper. Someone might object that we do not give a genuine causal role to non-physical consciousness at all. Instead, all the causal work is done by the physical correlates of consciousness. And where is experience generated in that approach? And Chalmers, another quote again, he says there are more radical approaches that allow consciousness to play a special causal role, but they don't want to go there. But actual theory does want to go there. Okay, so a quick recap. Their quantum mechanical wave function collapse math can be applied to any type of consciousness property, though, not only to integrated information theory. And it's generalizable to theories in which the consciousness property actually does something in the collapse process, not only triggering collapse. So actual theory approach to property dualism is postulate a new property. We call it noetic charge. Noetic charges emanate noetic fields that instantiate experience. Noetic fields generate conscious agency. They play a causal role in the collapse outcomes. Okay, a little bit of history of the introduction of new properties in reality theory, in physics. You had Newton's laws of classical mechanics, approximately 1687. He introduced the property of universal gravitational mass that's acted on by the force of gravity. Then Maxwell's equations, electrodynamics, approximately 1862, introduced the property of electric charge is acted on by the electromagnetic force. Then quantum mechanics, the development of quantum mechanics, introduced the wave nature of matter, but that's not really a new property. But there was introduced the property of flavor that's acted on by the weak nuclear force, and the property of color charge that's acted on by the strong nuclear force in the 1970s. And now we're introducing the property we could call it noetic charge, which is an ontic property of matter that instantiates experience of being. It's not involved in any forces, though. It's involved in the collapse process. So noetic charges generate noetic fields on this view. And noetic action is noetic field-induced collapse. So the noetic field-induced collapse is the measurement or knowledge of the system. That's why it collapses, and also influences the result, but remains consistent with Born rule, I'm going to suggest. There's another quote from the Chalmers paper where basically they set out this possibility and conclude, though, with we do not find this picture essentially especially attractive, but it's at least worth putting it on the table. So this approach is to move that further forward on the table. 5 minutes, thanks. Okay, so in addition to generating experience and conscious causation, possible noetic field generated systems on this view might include Platonic ideals, the acupuncture chi meridian system of traditional Chinese medicine, which influences the biological functioning of the organs of the body, or the chakra nadi system of traditional Indian Ayurvedic medicine, or systems of nature spirits of traditional religions. On this view, the physical structure of a biological or other entity constrains functional possibilities. the noetic field systems supplies unity and continuity of experience with functional effect, however, only where possible through collapse on this model. Possibly that's what Niels Bohr was talking about when he quipped once, there's a perfectly good place for metaphysics. So this view can make sense of paintings like Alex Gray's painting here, which shows the physical body and the mechanical chemical systems of the body, and also what actual theory is calling the non-physical bodies or consciousness-like noetic field systems as well. Could noetic fields generate the great panoply of phenomena we experience? Well, analogously, consider the panoply generated by the simple Maxwell's equations, electromagnetic fields. Everything we see, everything we experience is generated by the simple Maxwell's equations visually, electromagnetic waves. That's an analogy. Okay, on this view, noetic field dynamics operate according to metaphysical, psychophysical laws or rules that need to be identified and made precise and need to be made testable. And going beyond, in the kind of a next step, we could postulate a not empirically manifest domain that interacts with the noetic fields domain. And maybe something like the soul could exist on that domain. And there have been a serious approaches to the philosophy of science, like Roy Bhaskar's meta-reality, that have had this view as well. Many have warned about how strange this approach will be when the actual theory is come to be known. My favorite quote is from Anton Zeilinger. This new theory will be so much stranger than current quantum mechanics that people attacking quantum mechanics now will long to have it back. Zeilinger. Conclusion. This meta-ontology can sustain the conscious causation problem, mechanisms for biological functioning throughout nature. The models need to be made precise and made testable. And although it's called dualism, it's also in a sense dual aspect neutral monism and non-dual in that way. So support these projects by contributing to CIHS. We're a 501c3 accredited university, and by helping develop this model. I could if you're a theorist or experimentalist interested in this approach, I'd be interested in talking to you to help advance it.
You saying all these wonderful things just comes about because the noetic charges cause quantum measurements. That's the only function of noetic charges, to cause quantum measurements. That's what you said.
No,
I heard you say that earlier on.
Oh, well, maybe I mixed up something. I was complaining about Chalmers and McQueen's paper, where all their model does, all their consciousness property does, is collapse the wave function. It doesn't do anything. But they say that an approach where it also does something in the collapse process is possible and worth investigating. And this approach takes that approach where the outcome of the collapse is affected by the noetic fields.
So they function by choosing options, quantum options.
Yes, yes.
So the world becomes a little bit more classical with every quantum measurement. And so you're guiding that. The noetic charge chooses specific quantum outcomes. That's the main function of it.
So on this view, noetic charges generate something called noetic fields. And the dynamics of exactly how noetic fields operate is not determined yet. but they do help guide the collapse outcome in specific events. So rather than the collapse outcome being purely random within the probability distribution, in some cases on this view, there can be a selection. That's where conscious agency happens.
Comment and a question. The comment is just in the way that you talk about the causal closure of the physical. It's worth pointing out that our collapse theory, like most collapse theory, does violate energy conservation. And so perhaps the correct way to respond to this worry about the causal closure principle is not to say that these theories do restore energy conservation, but that they're not needed. It's not needed to restore energy conservation anyway, since we've got collapse theories that just don't. So that's just a comment. And then the question would be, I guess I was wondering, why do you see this as expanding upon what Dave and I have done, as opposed to just what, say, Eugene Wigner has done? Because it looks like I can see what you're doing as expanding on Eugene Wigner's approach, the idea that consciousness causes the collapse of the wave function, and you want to oppose our attempt to understand consciousness in terms of this mathematically precise property in integrated information theory, and understand it differently in terms of noetic charges. So that would be the question.
Good, thanks. On the comment, thank you. And I think that's a correct point. But the selection among different eigenstates of the collapse outcome, they all have the same total energy. So that doesn't violate conservation of energy. But the rapid collapse, like in the consciousness causes collapse model, that does involve some energy difference. On the question, I'll pull out the part about being mathematically precise. I like that about your approach, and my hope is that this approach can also become mathematically precise as well.
I'll be brief. This may be more for Kelvin than for you, but if consciousness is Tononi IIT and causes collapse at a distance, is it non-local? Are you using a field like he uses it, or is it a quantum effect in Tononi IIT that's causing the collapse? So the wave function is spreading out to the conscious observer, so the conscious observer doesn't have to project onto the collapse, onto the wave function? The conscious observer is within the wave function, and that wave function is spread out over a distance, and it collapses everywhere simultaneously. But you have the observer's consciousness, then you have the wave function. The observer's consciousness is caught. You don't have an observer. But the wave function is what the consciousness is causing to collapse. I don't get it.
Thank you. Okay, so our next speaker is Josella Stroo, who's going to talk about whether quantum physics can enable free will.
Can quantum physics enable free will? Yeah, that you said that I will talk about that, but I have a surprise for you. Because Friday I was sitting in a plane to here, and I thought, okay, maybe there's a message that's more important to share with you, and I will touch upon the topic of free will. But the main thing will be maybe about something else, because there I was sitting in a plane and everyone was around me was watching movies, and I thought, well, I don't enjoy that too much, watching movies, but what do I enjoy? And that's actually watching videos about consciousness, and particularly in combination with quantum physics. So I watched this, what already was mentioned, Consciousness and the Collapse of the Wave Function video of Kelvin McQueen and Dave Chalmers. And actually what's kind of surprised me in the end of the video of Chalmers was what he was saying, and that was this. It's hard to do interference experiments on the human brain. And with interference experiments, he probably means things like the interferometer that James Tagg was talking about. Probably the brain wouldn't survive it, he said. And then I thought, well, is this really true? Or is this just such an intuition that people have that we cannot do any quantum experiments in real brains of real humans being alive? So that's what I was wondering. Can the human brain survive a quantum experiment? And actually that was already my mission for the past years. My mission is to figure out what quantum brain experiments we can currently employ with state-of-the-art technology without damaging our beloved brain. So that's what I'm working on. What can we do? So we start with the technology. What is currently available, and what experiments can we think of? What is actually the edge of what is possible? Can we send photons through the skull without destroying the brain? Can we maybe measure the reflection of photons that went through the brain to start with? And actually the answer to this is yes, we can. It's already done a lot in neuroscience. And that's named near-infrared spectroscopy. And it's, for example, used, as stated here, for detecting intracranial bleeding. So what's basically done is sending this laser light through the skull into the cortex, and there they measure the reflection and how much is absorbed and how much is not absorbed. So in neuroscience, there's a lot of knowledge. In quantum physics, there's a lot of knowledge as well. And what if we combine those two fields? So all the things they use to measure signals in the brain, this noisy brain, they have a lot of knowledge about that, how to get along with those signals. And on the other hand, we have quantum optics, the part of quantum physics that's dealing with light as quantized light, so photons, and they have those really, yeah, I always am impressed. 1 month ago, I was in a lab of quantum optics, and I'm always get impressed by those really great laser lights and everything. So well done. So what if we combine those two fields? Can we find those experiments in the brain, quantum experiments that we can do? And actually we have a lot of methods at our disposal, and we are making now lists of, I think we have more than 70 methods already, how we can actually do this. Because of course we have this brain which is wet and noisy and is not the ideal circumstances for quantum experiments, but still there are options that we have. And even at quantum optics, we have a lot of options. So this is some of the methods that we're figuring out. Will that work or will it not? They have in neuroscience, they have methods to divide between things that are reflected by the skull and the signals that went through, for example. And on the other hand, at quantum optics, they have ways in which they do a measurement, but they don't destroy the superposition, for example. What if we combine all those methods? So that's what we are working on. What can we actually do with human brains, human consciousness? So one of the experiments that we are currently thinking of is this one. And I made this figure for you. And you probably recognize the interferometer here. Can we do this experiment, this interference experiment with actually, so there's a laser, a beam splitter, there are two paths, and they're recombining, and then we have a detector. And we are working with a professor who has his own quantum optics lab. And we were talking about this, and he actually said, well, there's a merit in doing this. Just as a starting point, see actually what signal do we get out if we do this. And we can, for example, select certain modes, so it's easier to get the right signal out, and that we don't have only noise, but really have some signal. And even, does the signal change when you're conscious or not, or if you have certain thoughts? So that's what we want to figure out. And we, of course, use such a cap, which is used during NIRS as well, and all the, so fiber splitters. So you have a fiber which goes through the skull, and the other one detects it. So this is the conceptual idea, actually, of one of the experiments we are currently working on. And the other one that I want to share with you, and it's actually the first time sharing with you this experiment. We just finished, not finished the experiment, but finished the first part thinking about it. And we thought, okay, maybe this is a good time to share it with the world. So we were thinking, what technology do we have? How can we use the technology that's currently available? Because, of course, they're making this fancy quantum computer-like machines, and they're awesome. And of course, there's some spin-off technology that's available off the shelf. And that's what we want to use. And for example, this is an entanglement source. Some decades ago, they couldn't believe, I think, that we now can buy such a thing that entangles two photons. Actually, at how it works, it splits the wavelength of one photon in two photons, which have the double the wavelength. And so you get the wavelength at around 800 nanometers, and that goes through the skull. So that's what we need. And so this device actually does that, entangles the photons, and we have two photons. We can send one to the brain and one to something else. So that's what we wanted to use. And now the question is maybe I hope you are not coming here only for the free will part, but here is the 1 minute about free will for you. So there are, of course, many reasons why people want to do those quantum brain experiments. And one of the reasons is maybe to find out, do we have free will or not? And as people have talked about already about the causal closure, a lot of in physics is, okay, this reacts, and then this is the what comes after. And one of the options, one of the things in physics where that doesn't happen is when the wave function collapses. So in the gray area, it's the wave, the probability you have, and when it collapses to a certain position. But the question is, why does it collapse to that position and not to another position? Do we maybe have some, as a conscious being, do we maybe can guide that position a bit to somewhere else? That's what we want to research. And what will that lead to? If we are able to do that, maybe we can increase the variance a bit of the probability, or maybe we can shift the mean. Yeah, that's what we want to find out. And actually the link of the video, 4-minute video we made with a very easy explanation about this on YouTube is in the book that you have about the conference. So you can watch there the other minutes about free will. So that's one thing that we want to research with this. And so the second experiment that I want to show you is actually based on entanglement. And entanglement is, well, James Tagg said, superposition is very easy to make. Well, entanglement is getting easier to make as well. Currently, they're working on, I'm from the Netherlands, and they're working on making a quantum internet and entangling photons between The Hague and Delft, around 10 kilometers apart. So yes, it's difficult to entangle those photons, but it's getting easier and easier. So maybe we can even use that for the brain. And we were thinking, okay, what is the easiest experiment that you can think of? And that's what we came up with this. First, we had some more difficult experiments, more complex experiments, until someone said to me, well, complexity is a sign of weakness. So I thought, okay, what's the first most simple experiment we can start with? And it's not simple at all, of course. But what we want to do is to entangle two photons with probably with a source that you saw already, that we can buy. And then one photon we will send to a detector, and the other photon we will send to the participant. And the thing is that there are all theories about, can conscious collapse, and when can consciousness have influence on when it collapses and even where it collapses to. So that's the question, and that's actually what we want to research with this. And of course, it's not easy, but we want to try it. And so the idea is, hopefully you get the idea by this picture. I hope I make the picture in a way that you at one of you already understood it, but so the idea is, if the participant has a real influence on the collapse, that you actually would see an effect at the detector, because those are entangled, those photons, so they have a relation to each other. So that's the idea. You can even put, for example, a double slit on the left path, so you can see, okay, can this interference pattern, will it change if there's a participant versus there's no participant? If you just put a dummy head or nothing there, does it change? And the beauty actually of this experiment is that we just send the photons to the brain, and we don't, they don't have to go through, and we don't have to measure reflections and stuff like that. It's just, it can get to their entangles, and then we want to see, is there anything special going on as a detector? And maybe it's not, there's a chance that we don't see any special things there, but on the other hand, if there is something special going on, that would be great. I think we really need some new data to get further in this field actually of quantum, because there are quantum brain theories like we saw yesterday, and I think it's great if that expands. And at the same time, it would be great if the quantum brain experiments would expand. And of course, it will start with a lot of failures because it's so hard. But I think if we combine all the knowledge we currently have, we have some chance of succeeding in doing this. And you might wonder, okay, nice ideas. Are you doing already actually some stuff? And yes, we thought, okay, along with working on the mathematics and stuff, we're trying, starting off with experimenting with lasers and see how that works. So we here have programmed, so we can activate the laser actually, and we can set all kind of values there to exactly to what we want. And then we put in, see if that star works. Yeah. Yeah, so maybe this works. Yeah, okay, I will leave it like that. So we have the laser and at the right wavelength, so it can go through the hand, even it reflects. And there we have the slits, and we're using double slits, single slits, and there we have the detector. And we're now, playing a bit around with it and see if what we measure actually is the same as what we calculated. And now we want to add an entanglement source, and of course it gets more complex. And then we, just step by step, taking the first steps in trying to do the world's first quantum brain experiment. Maybe it's done, but as far as we know, it's not done yet. So yeah, that's. This was this is a slogan actually. Let's start failing, because there will be a lot of failure. It's not het is niet voor niks dat dit nog niet gedaan is, they say in Dutch, but what it is in English, I don't know. It's no surprise that it hasn't been done yet, because it's so complex. So I thought, okay, let's start failing. And it would be cool, I think, in maybe some years on this conference, there will be presenting here more people on their trying to do those quantum brain experiments. So if you want to be part of possibly the first successful quantum brain experiment, maybe you have some knowledge available or other resources, you can contact me. My name is Josella Stroo, and this is my email address. Thank you.
Thank you. As you know, we've been doing quantum optical experiments on the most important part of the brain, the microtubule. At least but that's not the whole brain. That's not what you're after. But there's another technique was done by a guy named Pierre Saint Hilaire, where he used a laser into the eye. And the retina in the back of the eye is part of the brain. And if the brain's holographic or consciousness is holographic, you might get information back out. And he actually started doing it on himself. And if you do it right, the laser isn't harmful. And it got some interesting data. What it meant, he didn't know. But then apparently his wife tried it, and she had kind of a bad trip from the effect of the laser into the eye. So you got to be careful about that.
Yeah.
But that might be a way to go.
Yeah, great. And it would be great to, the Scholes lab is doing it, right? On the microtubules.
Scholes lab and also Daguerreo's lab in Central Florida.
Yeah, it would be great to work together maybe on some points if they use their knowledge to actually use it for the brain experiments. Yeah, would be great. Yeah.
So I want to make sure I understand this right and what you're looking at. The human in the one graphic you had, the human could be the person reading the detector, because we want to know whether the collapse occurs when the measuring device measures, or when the human reads what the measuring device measured.
Yeah.
Are we also looking at the human as a measuring device?
Yeah,
or both?
Good question. Yeah, I think there are two different setups. If we have the setup ready, we can easily switch between those two kind of experiments. Is there if the participant actually can look at the screen, does it make sense, or can it even change it without looking at the screen? You even have some neurofeedback methods where the participant is looking at the screen and it's trying deliberately to change what is on the screen, for example. So that are different ways to go for the experiment. Yeah.
Hi.
Hi.
My background's a bit different than the neuro stuff. I'm from material science and I have some physics backgrounds. And one of the experiments that I was involved in, or not directly, but it was part of my advisor and I had a lot of exposure to, was sort of getting a video with the transmission electron microscope of like shooting a pulse of electrons at a nanotube and sort of capturing the pendulum kind of motion. And it was a sensitive experiment. I mean, we had to like sort of repeat with one picture each time over the course of like a week because you didn't want to break it. And you had to capture this video and reconstruct all the individual pictures. And it sort of reminded me of another thing that Dr. Cook was talking about stimulating specific neurons to trigger episodes. So you trigger a video or something, and possibly you could sort of have one laser simultaneously with the next one, probing by a different delay and capturing different moments, maybe. I'm sort of abstracting a little bit. But in terms of just on your experiment, things that you look for, like what you said with seeing if you could trigger a change in the video you would see on the screen, I'm just trying to understand like what are sets of things you could look for where you could say, oh, this is definitely quantum, or like, oh, this might be a cool quantum thing that I could collect from my potentially quantum results, or what would that be for you?
So if we see that the probability, actually the probability wave that we have, if that changes, that would be really,
So
striking result.
say you did that one thing repeated 100 times or something, would you talk about like a frequentist type of probability where you would say like—
What kind of probability?
Where 29 out of like 100 outcomes you would associate to like a frequency probability, which if you repeated it with some change, that you're determined to cause it 67 times out of 100 times. Is that what you mean by like a change?
Oh yeah, or just changing the shape of the probability, things like that, or any changes. It's a bit, the experiment is a bit open for all kind of fluctuations we can add and see what happens on what we can detect, and of course,
Well, thank you. That's a good starting point.
Thank
and
you.
thank you for the talk.
Thank you. Hi.
I didn't hear very well, but so this may be overly simplistic or whatever, but I'm curious as to what these experiments would not be able to disclose about the brain, and that so many of the questions in this conference are about consciousness and how that relates to the brain. So what are the primary limitations of this type of investigation? The starting point, it seems to me, is that we are conscious and we don't even know how that relates to the brain. So what goal and what's the limit of the goal do you see in this?
Great question. Yeah, because probably a lot of people here believe that consciousness is not only in your brain, but extends to maybe something around your body, of even outside that. And but at the same time, a lot of people here believe probably that you kind of having a body adds something to your life, to your experience. So how I see it is that with having this body, it's a bit fragile. As humanity, we're facing all kind of existential risk. One day the sun stops shining, and as long as we are tied to this biological body for experiencing, it's fragile. So I think we definitely need a better understanding how this consciousness relates to the body in order to get the best out of it, and see how we can employ engineering, maybe to maybe have some artificial body maybe one day. But I think that we want to keep our bodies. So, but as long as we don't know exactly how consciousness relates to our body, it's hard to see a future where we can really get the best out of the experiences that we have. And so thank you.
Okay, our final speaker for the day is Thompson, who's going to talk about getting measurements to do something useful in cognitive psychology.
Okay, we've heard a lot about quantum measurements in this session and yesterday, and most of us think of it, the main function of quantum measurements is to make quantum physics a little bit more classical, which I think is a rather boring thing to do. So I'm going to propose something that can be useful for cognitive psychology, and if it's useful, it means we can test it and so on. And so this is, I'm going to design what I call a quantum-like epistemic engine. Epistemic engine can be regarded in many ways. You can, if you're a materialist or a quantum physicist, you can think of this as a quantum computer stuck in some microtubule somewhere. But if you believe in consciousness or dualism, then you can take the epistemic engine to be something like a sensory mind connected to the brain. And so this is a speculative theory proposal. I'm going to discuss the two issues. We've talked a lot about the quantum measurement problem, and I'm going to talk about how this is similar to the sensory recognition of external objects. And I'm going to show what some of the simplistic solutions have been proposed for these. And I'm going to show that if we could have some ideal solutions, number 3 here, these two problems could be solved in a very similar way. And maybe you can use quantum measurements to solve the recognition problem. And so I'm going to design in an ideal world what this quantum-like epistemic engine would do, how it would function. It's going to, as a preview, I'm going to use joint quantum measurements between neurons in this thing so that its quantum probabilities represent credences. So you can do Bayesian analysis. And then it's going to be rather slow to start with. So I'm going to make a proposal, a small amount of new physics, which would make a big difference to the performance. And so that if this performance is what you want, and then this is a testable prediction. So we've seen a lot about quantum measurements in these sessions. The classical wave has effects everywhere. A quantum wave has effects at one place. And you can draw pictures like this. The previous speakers had their own pictures. And there's been a number of simple solutions proposed to make life more classical, the maximum distance, maximum energy difference, etc. But the trouble is it's very difficult to detect these limits experimentally. And in fact, most experiments to measure these things discover that quantum physics does quite well. You never actually find these limits except by decoherence. But I want to connect this to the to the sensory object recognition problem. So humans and animals recognize visible objects very quickly, within 1/10 of a second, 100 neural steps. So you can, the top row, you can recognize cars in any orientation, any distance, any background, but the bottom row is not cars. And so how is this done? If I look at you, I recognize people in here, I recognize chairs, a projector, all these things, just a quick glance, I recognize these things very quickly, and it seems amazing to do it. I mean, of course, you can do it with modern computers if you have big GPUs and do 1,000 million steps in a GPU on a gigahertz timescale, but our minds or our brains, whatever, don't seem to be doing it like that. So I've jumped ahead a bit here. There are two kinds of proposals to do this measurement problem. You can do it progressive extraction of abstract properties, or you can do predictive coding, predictive processing mechanisms. But both of these, as I just said, require lots of neural computation. And if we could do something quicker using quantum physics or using a modified quantum physics, then we might have some new ideas which could be tested. What I'm going to show next is that these green refers to quantum and blue refers to sensory observations. So we've got two kinds of observations. We've got quantum observations, which is the quantum measurements, and we've got sensory observations, which is observing a chair or some object. And maybe these are, if they're similar, maybe that's an aspect, both aspects of a new kind of event with joint physical and epistemic effects. But there's what I call a probability gap. If you just use standard quantum physics, there's a problem with speed. So let me summarize the similarities between ideal solutions to the quantum selection problem and to the sensory selection problem. Both of these problems have if there's an ideal solution, it selects upon many alternatives that are already there. A quantum measurement selects among the different probabilistic options. And a sensory shape, if I'm going to recognize a chair, I select that particular shape among all the possible things that could be on the floor in front of me. It could be an elephant, I recognize that. Well, it's very rare and improbable, but there are very many things. And furthermore, both of these selections select alternatives between configuration spaces with very many dimensions. The entangled particles have 3 dimensions for each particle. So if you think of all the particles in the air or all the, there's a lot of dimensions, but quantum measurements apply in these multidimensional cases extremely quickly. But recognizable objects have also very many possible transformations. These chairs could be arranged in another way, and I'd still recognize them as chairs. And if I move up close to them, I still recognize them as chairs. And both quantum measurements and sensory object recognitions appeared to be quite fast in the sense that some outcome just pops into existence. If you have a quantum measurement as a projection operator, then it works quite quickly. I mean, it's the reduction of the wave packet gives just one grain of a film being exposed. The selection appears to go very quickly, and our sensory mind can also recognize objects, especially dangerous objects. They've been selected evolutionarily for that. Now, I'm going to skip over this slide, but I just want to show that Bayesian analysis can be applied to describe both of these processes, or conversely, both of these processes can be regarded as implementations of Bayesian analysis. And Busemeyer's papers, there's a new paper he had out this year. One of the previous speakers showed that in one of yesterday's talks. So both credences for observations given evidence of the sensors can be written in the Bayesian formula, and quantum measurements, if you do a straight preparation and then do a second measurement to measure the hypothesis probabilities, you can show that also follows Bayesian rules. And I also want to show that quantum correlations can be built up in such a way that you can use a quantum system, a quantum state, to describe the correlations between all the objects in the room, all the possible objects in the room and their appearances. So it's, as many speakers have said earlier, it's very easy to make entangled states in quantum physics. So I'm going to imagine making an entangled state here, a correlated sum of all the possible hypotheses H for where the objects are and their appearances, the evidences where they would appear. And so by doing a measurement on this quantum state with the evidence that the eyes have before them, you can project onto that, and then you end up with a distribution of the hypotheses. So this is a very quick way of getting information. Well, actually, it's not very quick, but it's a way of getting information out of an entangled state, and it's possible to set up in an ideal system, in an ideal epistemic engine. It's possible to set up these correlations in such a way that you can use it to recognize objects. But there's a problem that you end up with a factor of square root of n on the wave function, which means a probability factor of 1 over n, all these possibilities. It's actually rather slow. But I'm going to go ahead and I'm going to try and see if I can use a system which has these quantum measurements, these two quantum measurements, and in such a way that I can make an epistemic engine like an analog quantum computer. It's not going to be a digital computer, it's going to be an analog quantum computer. And I'm going to use its wave functions to describe credences, so we can use it in cognitive psychology and do all the cognitive psychologists who show that the mind recognition processes seems to operate as if it were implementing Bayesian analysis. You can do that by using these quantum wave functions. And this quantum-like epistemic engine interacts with the neurons in the brain. And I imagine, following Chalmers and McQueen, that the brain already has quantum measurements in it, which make qualia or sensory evidence to be these superposition resistant qualities. So the brain, the function of the brain in this system is to produce projections onto particular sets of qualia. So I imagine that the brain can, in my head, produce the qualia of everything that I see in front of me. And then I want to use this this measurement that goes on in the brain to connect to this epistemic engine. So this epistemic engine, which is, you can think of it as a quantum computer somewhere in the world or somewhere, it has an initial state with a large number of stored contributions. And then you apply two measurements to this quantum computer, or this quantum-like epistemic engine. You apply a measurement that the brain does for the particular information from the senses, and I want the brain measurement simultaneously applies to this quantum-like epistemic engine, so that the quantum measurement is a way of transmitting information from the neural system of the brain to this quantum computer. And then a second measurement on the quantum computer then selects what the objects are seen. So this is an extremely simple way of setting up a quantum computer, an analog quantum computer, to do object recognition. You set it up with all the correlations between objects and their possible views, and then you project onto the possible views using information from the senses. And then you do a second measurement and it picks up what the objects are. However, there's a problem in normal quantum physics. This is very slow because of this 1/n factor. All these measurements in this quantum computer are random. So you have to, it randomly selects all the possible things and it goes through all of them, and you have to repeat it many times until you find the object that you see with your eyes. And so this is rather slow. But now I'm going to, sorry, I missed out. I'm going to speculate, I'm going to make a proposal for a new way in which quantum measurements work. I'm going to say that there's a joint measurement between this quantum-like epistemic engine, this quantum computer, and neurons. So the probabilities, there's a joint measurement. So the quantum measurement applies to this quantum computer and the neurons simultaneously, but the probabilities are determined only by on the neuron side. So this is a way of transmitting information from the neurons to this quantum computer. Senses determine sensations. Normal quantum theory, the probabilities are determined by both sides. So this is an asymmetric measurement, and the fact that this is not standard quantum theory anymore is why I use the quantum-like epistemic engine. So I'm trying to design a quantum computer which works in some space which we have to work out, which does object recognition very quickly, and it's coupled to the quantum system of the brain by these joint measurements. So this is rather speculative, I agree, but you could imagine, if you go back to the standard quantum physics. This is something which could be done using these quantum computers we've seen pictures of earlier. But I'm going to say that if living organisms or conscious organisms could recognize objects very quickly, and they do seem to be able to recognize specific things in their field of view much quicker than we would expect from the neural speed in the brain. If we accept that that happens, then this could be one explanation for why we recognize objects. And so this means that this quantum-like proposal, because I've changed the probability slightly in the joint measurement, I have to go back to what's called Gleason's theorem, which is what's used to derive the particular probabilities. But Gleason's theorem assumes that you just have one system. You don't have two coupled quantum systems. So there's a get out there. So because this quantum-like proposal changes the probabilities relative to normal quantum physics, and if organisms did use something like this for sensory processing, then these different probabilities could be tested using information from sensory psychology. And in fact, sensory psychologists have been doing tests and measurements on object recognition and sensory and oral recognition for the last 150 years or more. And so there's a lot of information which is in need of a lot of information which is in need of explanation. So normally physicists such as myself, my day job is in nuclear theory, do not change the basic probabilities. But since there's no particular fixed theory for quantum measurements, it's still, quantum physicists do not know exactly when quantum measurements occur, although Kelvin and David's theory is an attempt to make a prediction for that. So I feel that I have some capacity to change this principle for this particular case, which would be very useful for living organisms if they had access to a quantum system like this to do object recognition. And so you can ask, where is this quantum engine? And it has to be connected to the brain, and so that it has the joint measurements affect both the brain and the system. And it has to be it has the same problems as quantum computers. You have to isolate them, so it's an implementation problem. So it could be within microtubules within nerve cells, or it could be within the what string theory calls extra dimensions or bulk space. Or it could be in some kind of new mental space which hasn't been discovered. And so in that case, it would be like another plane or another conscious level of reality. So that you can, whether you're a materialist or a speculative physicist or someone who's even more adventurous, there are different ways of implementing this. But I think we can calculate this model can be formulated using quantum mechanical wave functions, and we can model what goes on, and we can test the functionality, and then we can see whether where it could be. So to summarize, I've proposed that somewhere connected to our brains is a quantum-like epistemic engine, a quantum computer which has the particular function of being an epistemic engine. Paul Churchland used the phrase epistemic engine in about 1979. And it has the features that it uses quantum mechanical probabilities to represent credences, which those of you in cognitive psychology and machine inferences will know about credences. And it uses a correlated initial state to store all the epistemic correlations between objects and their appearances. And then it relies on the fact that neurons in the brain cause quantum measurements, perhaps as Kelvin and co. have been proposal. But I'm now going to say that when measurements in the brain occur, then there's this new connection, this joint measurements between the brain and this new epistemic engine. And if that is possible, then we get this very fast selection of objects recognized that we see when we look around, and that we do see objects very quickly when we look around. So this is, in some sense, a proposal for linking quantum observations with sensory observations and their recognition process. So it's a speculative proposal. It builds on what some of us in the room have already been developing and as a solution to the quantum mechanical measurement problem. But now I want to go further and work on another level and see how a slightly modified version of quantum measurement could be very useful in the sensory mind for cognitive recognition of objects. Thank you.
Thanks for an interesting talk. I still don't understand why, for example, it takes about 200 milliseconds, if not mistaken, if you're exposed to a face until you actually see it.
Yes.
And from what I understand, say recent research by Doris Tsao on face recognition, for example, shows that it's an extremely efficient system, and it works exactly with feature detection, but you have about 50 different
but do you
features,
have
and it is enough because of connection and scheme that to measure from something like 200 neurons to be able to predict which face a primate is looking at. I don't think there are any time problems that 200 if 200 milliseconds is not enough. I'm curious why. That's
well, there seems to be built-in neuropsychology to recognize faces. A number of people in this meeting have talked about that. But I'm thinking about recognizing elephants or motor vehicles if they come into the room. That's extremely improbable events that we have no preparation for, but we would still recognize them. You know, so and there's a scale invariance, which is a puzzle. When I move towards a chair, it doesn't change in size, even though it gets bigger in my eyes. There's lots of problems about speed and invariance in sensory recognition. It's not even clear how the brain does in scale invariance. That's one of the puzzles.
But there is some kind of linear decomposition of input, whatever.
I mean, machine learning people, they have these convolutional neural networks, but they're not real. There's no convolutional processes in the brain. Okay.
I'm thinking about Necker cubes, that sometimes you recognize it's coming out of the page, sometimes you recognize Necker cube going into the page.
Yes.
You can also force it. You can force yourself to see it one way or the other.
Can you force it? I have trouble forcing it.
It's not easy, but I think it can be done.
Yes. So you can change your priors. That's what the Bayesian people would say. You can bias your priors so you preferred to be one rather than another.
I'm just wondering whether there's an analog there with a Henry style use of free will in quantum measurements, where he thinks that you can apply your free will to cause the wave function to collapse in a certain way.
Probably.
So thinking about there's an analog there between quantum measurement and free will and recognizing things in free will.
It could well be.
I'm super interested in this asymmetry you're
Yes.
talking about. So it wasn't, you didn't define it really.
No, it means that the probability information goes from the brain to this quantum computer. It doesn't come back. The information has to come back by a different route, such as I talked about last year. So
it's sort of asymmetry in causality.
Indeed.
And so I'm just wondering if there could be an asymmetry in time, if there's some kind of, so that's almost a spatial asymmetry. Combined.
This is a logic. I haven't thought about asymmetry in time. I should well, yes.
Because I wonder if that can buy you. I've always wondered about these sort of pop-out effects and these extremely fast, sort of almost top-down, but not enough speed, not enough time to get a top-down effect, but it's still a top-down effect.
This is a proposal. If it worked, it would give very fast recognition.
Right, and so I'm wondering if you could get like a retrocausal speed up.
I'd need some persuading. Sorry.
Okay, so, and again, I want to kind of drop down a couple of levels of sophistication here, because I want to understand your quantum level, and you say epistemology, or what do you call it? I know what epistemology is, but it's
So just means knowledge.
right, right.
Epistemic engine is a knowledge
Epistemic,
engine.
yeah, okay, so your
You-
epistemic engine, that's like a big black box for me.
It's a
right
quantum
now.
computer that's coupled in a specific way to the brain, to the neurons in the brain.
Right, but what makes it experiential? Because you're talking about
Well,
a
okay.
chair and a machine.
I know.
A computer can sense
Okay,
it.
now you're getting to the interesting questions.
Yes, yes. So that's why
Okay,
I still
well,
see it as
first
kind
of
a
all,
black
you have to
box.
admit, your worldview has to admit that there are such things as experiences. And this version is compatible with dualism, well, substance dualism. If you want substance dualism, something like this could be used to explain how the mind and the brain interact with each other, how the brain transmits information to the mind.
Because a classic computer with proper sensors can already detect a chair better than you probably and tell you.
But yet it requires millions of steps to do so.
But that still doesn't know the essence of what it is.
No. So in order to explain where the appearances come from, you have to have a space in which, or a place or somewhere where there are experiences. And so that my option of having a mental space you would say that if there are forms in this mental space, then that is the visual phenomena. That's where the qualia is. You could take that view of the mental space option.
Just a quick abstract question. I apologize if this is out of your field. But I've been working on like knowledge management types of activities.
Yes.
And one of the problems that I deal with is like forming connections or indexes between like pieces, like atoms of information.
Yes.
And I was seeking out the possibility of potentially involving myself in like getting like a quantum computer and practicing the different ways you have to connect things. And I was wondering what you thought about the possibility of when dealing with this, actually being able to gain intuitions that would be useful.
Yes, I have thought about it.
Okay.
And in fact, my initial state, which stores correlations, can be regarded as a dictionary. Anyone who's done, and this fast method with these asymmetric measurements can be regarded as a way of associative memory, because a fast associative memory, because normally on a computer, associative memory, you have to look through all the words in the dictionary or have a hash table or something. Whereas, but psychologists have been saying that humans have associative memory. They've been saying it for the last 50 or more years, but they have no idea how to implement associative memory. And so if this quantum-like epistemic engine could be set up like this, then it would be a very fast associative memory, and it would be a natural way of using associative memory, because you could use it for many other purposes. Every time you look at a word, you have the meaning and so on. But it requires this biased probability to make you don't want to have just a random selection over the whole dictionary. You want the key to be known, and then you want to use that probability of the keys to look up the results. So it requires this specific kind of change to the probabilities. So a normal quantum computer wouldn't give you a fast lookup.
So just a quick follow-up. Do you think it could be useful for me to look at initial conditions while I'm trying to gather observation data on these notes? Because Nicholas Luhmann was the man who made this Zettel costume, which was a bunch of boxes and index cards connected to each other, and he had sequences of change of thought. and you just go through it from beginning to end and associate it, if it's in there already, or add it to the end if it wasn't. He sort of organized his thought processes based on this, but he complained about an issue of this massive associative correlations between all of the different cards. And I'm trying to understand a feasible way to try to, or not even completely, but just a beginning approach to try to capture those correlations. And I'm wondering, is this initial condition type of information useful?
Well, a quantum system with entanglement can be used to store an enormous amount of information. And we've heard this claim many times, and whether we're also said to be much easier than it used to be. So a quantum computer can be used to store lots of correlations as between keys and the text as in a dictionary. But the lookup process with normal quantum physics in a normal quantum computer is very slow, because you have to you look up and you get one at random, and you have to keep going until the key you want appears. So quantum computers themselves, I don't think are actually going to be very useful. That's because of this randomness approach, and because they have decoherence, and you have to repeat everything 1,000 times in order to get some statistics out. So I have colleagues working on quantum computers. They're much more optimistic that they'll ever be useful than me. I don't think they're going to be useful. I looked into it about 20 years ago. But
well, thank you for that. I'll definitely take a look into this randomness issue. So, thank you for the talk.
Okay.